Our third and final speaker really needs no introduction in this crowd. He's a longtime member of the board of directors of the EIPC. Martin Gaudian, or as we say in Germany, Gaudian, started his career with the company Textronics in the early 80s, where he was responsible for test engineering on the portable oscilloscopes, which were so important to Textronics' success and fame in those days. He joined Polar Instruments in 1990 and there designed a shorts locator for multi-layer PCBs. He became the CEO of Polar in 2010. Martin is a regular contributor to the know-how of the PCB industry through his active contributions in writing, standards work, and his constant support of PCB industry groups and associations. Martin will speak to us about the causes of insertion losses in high-speed circuits and how to design and to avoid unnecessary or excessive insertion losses, and will also give us some examples of how to test designs for avoiding excessive insertion losses. Martin?
Hello, Paul. Hello, everyone at the webinar. Pleased to be back, and would really like to be meeting in person. But yeah, looking forward to presenting this, and also a big thank you to both Manfred and Julie, because both of your presentations lead into what I'm going to say. In fact, I was thinking if everybody used Manfred's NF30 and Julie's HVLP5, then probably wouldn't need our tools anymore. So please don't make your materials too good, because we need to sell some software here. So this is really showing you the primary drivers for insertion loss on high-speed base materials. So I'm going to run through what the drivers are and then how to use a modeling tool, and it could be any modeling tool, but I'll use ours to show you how to model the insertion loss. And right on the first slide here, Manfred mentioned that when you're using woven glass, you can get some problems with the insertion loss. And right down here, the differential insertion loss. This was something Lee Ritchie pointed out to me, that there's a measurement here and there's a dip at around 30 gigahertz and 35 gigahertz. There are some papers that show that dip is a harmonic resonance at that frequency where the signal crosses the glass weave. So that's kind of interesting to see that on a woven glass. That's a measurement in real life showing you what happens when you have harmonic effects at certain frequencies on glass weave where you've got non-homogeneous base materials. But always like to get back to basic principles, and if we look at what we're used to dealing with impedance, the drivers for impedance, rather insertion loss, are the dielectric constant of the base material, the width of the trace, and the height of the trace above the substrate. So that's the main things to get the characteristic impedance of a transmission line correct. But if you're looking at getting the insertion loss, you have to look at different parameters. They act on the same line, but they're very different from those from impedance. First thing is impedance is independent of line length. No matter how long the line is, a 50 ohm line is a 50 ohm line, whether it's a millimeter long, 5 inches long, 5 miles, 5 kilometers long, it's always the same. Whereas the insertion loss is directly proportional to the length of the line. So a signal can be very strong at one end of the line, and the longer the line is, the signal gets very quiet at the other end. So a designer, when they're looking at how much insertion loss, there's a very easy thing to adjust in their design. If they keep the traces short, then the insertion loss will be low, and proportionally low no matter what base material you use. So short lines for insertion loss are good, but of course you can't always route a circuit with very short lines. So you need to know how long the line is going to be to figure out how much total loss there'll be in the design. Okay, so the longer line, more signal gets lost. But what causes those losses? And you've heard Manfred talk about the losses in the base material, and Julie about the losses on the copper. What we're going to do is break those down and show you how to estimate and model how much loss comes from the copper and how much loss comes from the dielectric. I'd like to take it back to really basic principles in that the loss forget about electronics. The loss is simply turning the electrical power into heat. So as we run at higher and higher frequencies, I've set fire to tan delta here. It doesn't hopefully get that hot normally. And if Emma's listening, she won't worry about flammability. But the higher frequency you go, the more power is lost through heat. And basically, each time you charge and discharge the laminate, as you go from a 0 to a 1 and back again, a small packet of the energy in switching from 0 to 1 is used in altering the charge of the laminate. The higher the tan delta, the more heat that gets lost. So obviously something like NF30 is going to have very, very tiny losses. Something like FR4 will have significant power losses through heating. So heating of the dielectric is one area you have to be concerned of. And it's very easy to model how much power is lost through heat. And it increases, the power loss increases linearly. So the higher the frequency, the higher the power loss, regardless of the material. The rate is obviously less in high-speed materials and more in low-speed materials, but the more frequency, the more power you'll lose. Then we can look at the track, and again, I've exaggerated here. I've got it so hot that I've melted that, and that's never going to happen in reality. But just to show you what's happening, the copper heats, and the copper loses power through two different mechanisms. One is the resistance of the copper, and the other is, as Julie so clearly explained, is the surface roughness of copper. Also, again, going back to Julie's presentation, as we ramp up the frequency, more and more of the current is taken on the outside of the conductor. So when you look at copper losses, they get progressively worse until the current is entirely on the outside of the skin of the trace. And here we've got at a gigahertz, you can see almost all of the currents occurring on the outside of the trace. And at that point, not only the current is occurring on the outside of the trace, as you push above that, the roughness starts to interfere with the losses as well. So copper losses are quite a bit more complicated than dielectric losses because they ramp up quite progressively in the lower bands and then they smooth out but continue to increase as the frequency goes up. So not as smooth as the HVLP5 foils there, but there's a microsection of some copper on a stack up here. Again, if you've got a trace where the roughness is higher on one side than the other, worth considering when you design the stack up, should you put smooth to smooth or rough to rough? And that might mean that things like strip lines, you might want to fabricate a differential strip line, a broadside strip line across a pre-preg rather than across a core, so you can swap the logic around for strip lines than you'd have for perhaps impedance designs. But copper roughness is important, and it's important that we model that roughness when we look at the insertion loss. I've just blown it up really large there, and again you can see, you know, on some earlier types of copper foils you get a really rough surface profile. So all the information you need to model the insertion loss is contained in the stack up. You contain the types of materials, the loss tangent, where the materials occur in the stack up, and whether you've got different types of materials within the stack up. It's quite useful to be able to take this and pass that information directly into a field solver. By using a field solver, and I'll use ours, but other solvers are available, you can find out which parameters have the largest impact on your design. So the first thing we talked about in the early part of the presentation was the line length. So your field solver needs to know how long the line is to calculate the insertion loss. And I've broken down here, we've got the conductor loss in red. In this case, I've set the trace conductivity really, really high. So I've just forced that to be 0 so we can just see the attenuation due to dielectric loss. And in fact, the blue and the green lines are sat on top of each other here. So they're directly on top because there's only dielectric loss is contributing to the attenuation. I've now set the trace conductivity back down to normal level, and we can look at the attenuation. And then sorry, go back now. I've set now the trace quantity to a normal level, and we can look at the conductor losses. So the copper losses now we're basing on a smooth copper. You can see the conductor loss and the dielectric loss, and then sum together total attenuation. So when you're looking at choice of material laminates, should I use a smooth copper foil or a very good base material, you can make a trade-off between whether you use smooth foil or whether you need to use smooth foil and a good material, or both. And also trade, well, if I could make this circuit half as long, would I need to use such an expensive base material? So all of those things can be modeled and experimented with before you actually commit to producing or making prototypes. We talked about the skin depth, and this is just a nice thing. The skin depth is nice because it varies according to frequency. The higher the frequency, the lower the skin depth, and that's the same for all structures, all constructions. You can see here that as we go up to 10 gigahertz, we're down to about 20 micro inches, 25 microns. It's about a micron at 1 gigahertz. The field solver just works that out automatically for you. There's no data to put in. It calculates, it works out the frequency and calculates the skin depth. Okay, there it is showing graphically up on the screen. As we increase the frequency, the skin depth decreases. Copper roughness is interesting from a modeling perspective because we can set the field solver to have smooth copper, and there's a couple of other methods here. We've got Hammerstad, which is a method which was developed in the early days of radar at the back end of the Second World War, where Hammerstad was looking for the machining grooves in microwave in microwave waveguides. But Hammerstad works quite well. But it is limited in terms of frequency, so there are some limitations with Hammerstad. But for lower frequency designs, Hammerstad's quite easy. You can add in the RMS roughness in the Hammerstad method and calculate the effect on insertion loss. But for more advanced designs, we now use the Huray model, and go in here. The Huray model uses input from a scanning electron microscope and works out the ratio of areas, the effective ball radius, the area ball count, and the number of balls in area to actually model the insertion loss. However, most PCB fabricators don't have the luxury of SEM, and actually after fabricating, it's not that easy to go back and strip the board apart to see what the surface profile is like. So you can actually use another technique called Cannonball Huray, which was developed by colleague of ours called Bert Siminovich of Lamsim Enterprises, and Cannonball Huray allows you to put the RZ mat and the RZ drum side and calculate the ball radius and give you a very good empirical estimate of the Huray parameters, and that allows you to model using Huray method the insertion loss owing to surface roughness. So when you put all of those together, the conductor loss for smooth copper, the conductor loss for rough copper, the dielectric loss, you can then work out a total attenuation with roughness. And here I've added a loss budget on the line for the maximum loss per inch that we want on this particular circuit. So by using a modeling tool, it lets you work out a whole range of parameters in terms of insertion loss before you actually commit to producing any finished boards. Okay, and that brings to an end my presentation. If you've got any questions, please do feel free to ask. And if you'd like to know more about measurement of insertion loss, then you can have a look at the Polar YouTube channel, and you'll find all sorts of things to do with measurement of insertion loss, modeling insertion loss, and impedance as well. It's thoroughly explained in the Polar YouTube channel. Thanks, Paul, and over back to you.
Thank you very much, Martin.
I have a question for Martin. What is the maximum frequency you can achieve with the microstrip design without having radiant loss? Same question with the coplanar design. Coplanar?
It's coplanar, yeah. I mean, if if they're well matched in a transmission line, you get very little radiation loss at all. Almost all of the loss is down to heat. So you only get radiation loss on a microstrip if you do something like put a slot in the ground plane underneath. So provided you've got a continuous ground plane underneath or a continuous ground plane along the side of the coplanar line, radiation losses are negligible. So they radiate very little. So that's why we don't model the radiation loss, because on a well-designed line, if a designer follows the design rules and doesn't route the trace over slots in the ground plane, then they can ignore the radiation loss.
Okay, thank you. I have another question for you, Martin.
Okay.
Can you please explain the resonance effect of the glass fiber grid at 35 gigahertz? First slide.
I can't, but I know a man who can. There's a very good paper which I can share. There's some quite good academic papers on basically harmonic resonance. It's when the wavelength gets close to the Mach space ratio of the glass weave on the underlying glass reinforcement. So it's something that doesn't occur on non-reinforced substrates. But there's a really good paper which I was sharing with Lee Ritchie the other day. Lee Ritchie told me about the effect, and I then went and researched some papers and found some good papers. So if the person asking the question wants to contact me afterwards, I'll find the paper that I shared with Lee. It's in the public domain, and then we can have a look at it.
Okay, thank you.